We invoke Occam's razor constantly in machine learning. We penalize complex models. We add regularization. We say simpler is better. But if you actually ask a machine learning theorist to justify that preference from first principles, you quickly run into a wall. Is simplicity just a pragmatic shortcut? Is it an ontological claim that the universe happens to be simple? Or is there a rigorous, mathematical reason why trading fit for simplicity is the only reliable path to generalization? Today, we're going to trace that justification all the way from the foundations of statistical learning theory, through empirical risk minimization, structural risk minimization, and into the actual mathematical machinery of regularization. We'll see why the classical framework doesn't just hand-wave Occam's razor, but actually derives it as a methodological necessity. And we'll confront the model relativity problem head-on, showing why regularization isn't a circular trick, but a clever search strategy that pays off even when the truth isn't simple at all. Let's start with the setup. In statistical learning theory, we're almost always working with a binary classification problem. You have an instance space, say images or feature vectors, and a label space like positive or negative. You draw training data independently and identically from some unknown distribution. Your goal is to find a hypothesis, a classifier that maps instances to labels, such that its true risk is minimized. True risk is just the probability that the classifier misclassifies a new, unseen example. But you can't compute true risk. You only have training data. So you compute empirical risk, which is the fraction of training examples the classifier gets wrong. The most natural learning rule is empirical risk minimization, or ERM. You just pick the hypothesis in your chosen class that minimizes training error. On the surface, this seems perfectly reasonable. But is it reliable? Does low training error actually imply low true error? The law of large numbers guarantees that for any single, fixed hypothesis, empirical risk converges to true risk as your sample size grows. But learning isn't about fixed hypotheses. It's about selecting a hypothesis from a class based on the data. The hypothesis that minimizes training error could easily be the one that overfits to noise. To guarantee that empirical risk is a good proxy for true risk across the entire class simultaneously, you need something stronger: uniform convergence. Uniform convergence means that the gap between empirical and true risk is bounded uniformly over all hypotheses in the class, with high probability. This gives you a what you see is what you get bound. If your training error is low, your true error is probably low too. And if your training error is high, you can trust that signal and know your model is genuinely bad. But here's the catch: uniform convergence doesn't hold for every hypothesis class. It only holds for classes with finite capacity. In the Vapnik-Chervonenkis framework, that capacity is measured by the VC dimension. The VC dimension is the maximum number of points that a hypothesis class can shatter, meaning it can produce all possible labelings of those points. A higher VC dimension means more flexibility, more ways to fit arbitrary patterns. The fundamental theorem of statistical learning theory states something profound. A hypothesis class admits uniform convergence if, and only if it has finite VC dimension. This theorem gives us our first methodological norm. If you want reliability guarantees, if you want to trust that your training error reflects your true error, you must keep your hypothesis class simple. You must restrict its VC dimension. This is a means-ends argument. Simplicity isn't a metaphysical preference. It's the necessary condition for reliable inductive inference under finite data. But there's a problem. If you follow this norm to its logical extreme, you end up choosing a maximally simple class. A class with VC dimension 0 contains only one hypothesis. There's no learning left to do. You've guaranteed reliability, but you've sacrificed approximation. This exposes the core tension in machine learning, the bias-complexity trade-off. You can decompose true risk into two parts: the approximation error, which is the risk of the best possible hypothesis in your chosen class, and the estimation error, which is the gap between your learned hypothesis and that best possible one. Simple classes have low estimation error, but high approximation error. Complex classes can capture the truth, but they suffer from high estimation error. They overfit. Classical ERM only addresses the estimation side. It pushes you left on the complexity axis, but it gives you no theoretical guidance on how to navigate the trade-off when you actually need a richer model. You need a rule that automatically balances fit and complexity. That rule is structural risk minimization, or SRM. SRM doesn't pick a single hypothesis class. It picks a countable sequence of nested classes, ordered by increasing capacity. Think of linear separators, then quadratic, then cubic, and so on. For each class in the sequence, you compute the empirical risk, but you add a penalty term that depends on the class's VC dimension and a weight you assign to that class. The learning algorithm then selects the hypothesis that minimizes this sum: empirical risk plus complexity penalty. Look closely at that penalty term. It's exactly what we call regularization in practice. L2 regularization, weight decay, early stopping, dropout, structural penalties in model selection, they all serve the same mathematical purpose. They penalize capacity. SRM derives this penalty directly from the generalized uniform convergence bound. When you minimize the bound, you're mathematically forced to trade fit for simplicity. The regularization term isn't an arbitrary heuristic. It's the operationalization of the theoretical guarantee. Now, you might be asking a critical question. The theoretical bounds for SRM are model relative. You have to choose the sequence of classes and the weights before you see the data. Doesn't that make the justification circular? Doesn't SRM only work if the truth actually lives in a simple part of your sequence? If the world is complex and you force a simplicity bias, aren't you just handicapping yourself? This is the subfamily problem, and it's the central challenge to any defense of Occam's razor in machine learning. The answer lies in distinguishing between ontological simplicity and methodological simplicity. The former claims the world is simple. The latter claims that regularizing is a reliable strategy, regardless of what the world is like. SRM's justification doesn't rely on the truth being simple. It relies on a property called luckiness. If you're lucky and the true distribution is well approximated by an early class in your sequence, SRM gives you a significantly tighter reliability bound than ERM on the full superclass. You get strong generalization guarantees for free. But if you're unlucky and the truth lives in a complex subclass, the reliability bound for SRM is only slightly worse than the bound you'd get from ERM on the full class. You don't lose much by trying. More importantly, the what you see is what you get guarantee saves you from blind overfitting. If SRM selects a hypothesis from an early class and the training error is low, you can trust it. If the training error is high, the sharp WYSIWYG bound tells you immediately that your inductive model is mismatched to the data. You don't get trapped in a false sense of security. You get a diagnostic signal. You know to pivot, to adjust your sequence, or to collect more data. SRM turns regularization into a controlled search strategy. It lets you explore rich hypothesis spaces without paying the full price of overfitting, and it gives you a reliable way to detect when your exploration has gone off track. This is why the methodological norm for SRM is different from the first one. The first norm said keep the class simple. The second norm says trade fit for simplicity. Regularization isn't a claim about the ontology of the data-generating process. It's a procedural rule that guarantees you can navigate the bias complexity trade-off with theoretical reliability, even when you do know where the truth lies. There are, of course, limits to this framework. The classical theory assumes a stable underlying distribution. It's fundamentally frequentist. It focuses on predictive accuracy rather than truth-finding. And modern deep learning has introduced phenomena like benign interpolation and double descent, where extremely over-parameterized models with zero explicit regularization still generalize well. Those phenomena demand a renewed theoretical appraisal of generalization. But they don't invalidate the classical foundation. They highlight why we need to understand it first. When you strip away the metaphysics, Occam's razor in machine learning isn't about preferring simplicity for its own sake. It's about recognizing that finite data imposes a hard constraint on reliable inference. Regularization is the mathematical mechanism that respects that constraint. It's the bridge between the fundamental theorem of statistical learning theory and the actual algorithms we run on GPUs every day. If you want to push past the heuristics and actually understand why our learning rules work, you have to sit down with the bounds. You have to trace how uniform convergence decomposes into approximation and estimation error. You have to see how structural risk minimization emerges naturally from generalized capacity measures. That's where the real justification lives. Not in philosophy, not in tradition, but in the rigorous trade-off between fit, complexity, and finite sample reliability. The research is still evolving. The double descent phenomenon, the geometry of overparameterized networks, the role of implicit bias in gradient descent, these are all active frontiers. But they all stand on the foundation we've just covered. Master the classical theory, understand the means-ends argument for regularization, and you'll be equipped to read the next generation of generalization papers with the right intuition. If you want to dive deeper into the mathematical details, the foundational papers by Vapnik and Chervonenkis, the structural risk minimization framework, and the modern analyses of luckiness and oracle bounds are all worth studying. The theory isn't just history. It's the operating system of machine learning. And once you understand how it compiles, you'll never look at regularization the same way again.